Free throw physics with Addison Shivansh.
Our investigation. To find the lowest possible angle for a basketball to swish or hit nothing but net going through the hoop from the free throw line, and to find the lowest possible angle to shoot the basketball to achieve this. We'll also need the velocities for this.
Here you could see me shooting the basketball. As you can see, I have to use a very unorthodox shot form to try and get the lowest possible angle I could do. And here is a slow-mo video of the ball hitting nothing but net.
So the formulas we need to use are the basic distance in the y direction, the change in the distance in the y direction with acceleration and velocity, the range formula, and the velocity formula when you don't have time.
So as you can see the diagram here, we have to assume that it's a linear path when the ball goes through the rim, and R is the diameter of the rim at 46 centimeters, and B is the diameter of the ball at 24 centimeters. To find theta, we have to do sine theta of equals B over R, which is 24 over 46, and just do inverse sine and find 31.4 degrees, which is the angle at which the ball has to enter the hoop to hit nothing but net.
So in this diagram, we just linked both the person shooting and the basketball entering the hoop. So the YF is 3.05 or 10 feet. The X is the range, which is 4.34, which is from the middle of the rim, not from the backboard, to the person shooting. And the Y initial is 2 meters, so that's where we're assuming the release point is. And then VI and theta I are just initial velocities and angles.
So the math behind it, we did a projectile motion problem, but in reverse, to find the final angle first, which is much easier, as you could see from the math we did earlier and got the 31.4. The two missing variables are time and the final velocity, and we want to find the final velocity. So we have to use x equals vx times t and manipulate the equation so that we find t.
And here we use the distance formula in the y direction, and we substitute with time as we found on this slide where t equals all that. So we substitute in, and we have the y initial, y final, theta final, and the range, and we solve for the velocity final, which is 5.85 meters per second.
And that final velocity is the component of Vx and Vy. So we also have to find the final angle, and doing this experiment in reverse was to our advantage because since we already found the as you can see on this diagram, the initial theta, which is technically the final theta, and the using the diameter of the ball and the diameter of the rim, we found that. So then we can use that equation to find the things we needed in the initial shot.
So our predicted values when we found out the VI was 5.85 meters per second, or well, technically the V final, not the V initial, but then we flip it. So then we got the components of that. The Vx is 4.99, Vy is 3.05. And as shown here, initially on the left, those are the values. We need to find the final values. But the Vx stays constant as there's no forces in the X direction, so it has to stay the same. The only thing that changes is the Vy final, so we just plug into the formula and get it. That's 5.47 meters per second. And once we get the Vy final and we have the Vx there, which is a basic Pythag, and you have both sides of the triangle, you find Vf to be 7.4 meters per second. Inverse tangent of that to get the angle of 47.6 degrees. Now we called it final here when it's technically the initial because we reversed it. So now because we reversed it, now we're the motion is from the shooter to the rim. So basically, if you're if your release point is 2 meters, you need to shoot it at 47.6 degrees at 7.4 meters per second. And this is the quick basic program we made to model the situation. As we can see here, I put in the numbers at 7.4 meters per second and the initial angle. And as you can see, it just perfectly clears the rim. Now it looks like it barely just skims it and that's because it is pixelated. It's not that exact, and I made it extend over just to show you that it clears the rim just as it passes through the basket.
And so the actual measured values in real life. So here you can see me shooting the ball.
Here, and then we're gonna get a distance.
That's the motion in, yeah. So the measured values. We calculated the distance and time that the basketball traveled between those specific moments that we just showed in the previous slide by using a scale of 1 centimeter representing 12 centimeters in real life by using iMovie and getting the small increments of time. So then, as you can see, we found the distance is 0.3 meters and 0.15 meters, and we use the distance over time to find the velocity. And the time that we got to using the iMovie was 0.038 seconds. So doing the distance, which is 0.3 meters, over the time, which is 0.038 seconds, you get 7.89 meters per second as the velocity. And in this case, it will be the initial velocity because that's when we're releasing the ball. And the angle we found was surprisingly larger than what we expected it to be at 60 degrees.
And also here we had to assume a linear path for the second, so also a constant velocity. And also, yeah, the quick basic program we made, as we see here, it overshoots it. And in this simulation, it would not even make it through the hoop. And that's because air resistance is not taken into account. Obviously, when you shoot the ball, there's air and rotation. But here, just straight up, no rotation and no air resistance, so it would overshoot it. But in real life, it wouldn't. Percent error for velocity was 6.7%. Percent error of angle was 26.1%. Now, percent error of the angle is like higher because it's extremely low. It's extremely hard to shoot a basketball at a low angle and still swish it. That's why for us it was at 60 degrees was the angle that we did it at, which isn't even that close to the 47.6. But for velocity, it doesn't make that much of a difference as the speed, like it wouldn't be that much of a difference if you shoot it that much higher or that much lower. However, though, if it's extremely low or extremely high, it could result in an air ball or just a shot off the backboard. But shooting at a higher angle would help you make it in more, where we kept shooting at a low angle and just we had to make it a higher angle to even make it in, as elaborated in the next slide.
So, real life shooting is much different than the calculated shots that we had in our experiments. So, shooting at a low angle is insufficient as one is more likely to hit the front of the rim and miss the shot. And it took us a lot of tries to even get close to this low angle that we thought was close to 47.6 degrees, but it was much higher at around 60 degrees. And it's extremely hard to shoot at such a low angle because your body normally wants to shoot the ball in a normal shot form, and trying to do that would end up in a higher arcing shot, which would have a higher initial angle. And to shoot it at such a low angle, you'd have to shoot it basically from your chest using two hands and just shoot it like a catapult. And most professionals, they shoot at a higher angle shot because it increases the chances of the ball entering the rim because you have a larger area of the rim, the surface area of the rim that the ball can enter into and clear it perfectly. And also it gives an advantage of making it hard for defenders to block the shot because higher shots have a higher release, which would make the defenders jump higher or even reach in and potentially get a foul or anything like that. And so shooting at a low angle shot would do the opposite. They would be very easy to block, and you probably wouldn't even be able to get a shot off without it, and it wouldn't even touch the rim.
So yeah, basically shooting the ball at a low angle is not recommended as it is inefficient and extremely hard. Even when we were wide open, it took us over 50 tries to get this. So it just shows how hard it is to shoot at a low angle.
The end.
Yep.